Hi, my name is David Heidikian. I'm the Chief Technical Officer at bluShift Aerospace, and I'm here to talk to you today about advanced sustainable propulsion of launch vehicles. So without further ado, there are three focuses of sustainability when providing launch services. Should include propulsion footprint, launch vehicle design, and the carbon footprint of the rest of the business. By some measures, propulsion system development is more than 2/3 of the overall effort in developing a launch vehicle, but possibly even more than that of the overall environmental impact. The propulsion footprint includes propellants and consumables. It plays a major role in the sustainability of operating a launch services. All the things that can be burned, vented, and destroyed during a typical rocket launch are included in the propulsion footprint. If you exclude reusability, then vehicle design will impact environmental sustainability to a lesser extent once propulsion strategy is finalized. However, if you include reusability, then the vehicle design becomes a major player in the sustainability of a launch service. And finally, you have the business footprint. The environmental footprint of the space launch industry is negligible when compared to agriculture, energy, or industrial manufacturing today, but it's not negligible when considering that the industry is destined to grow by 20 times in the next 10 years. We should start now by pursuing minimalist design and by minimizing waste and minimizing fossil fuel utilization within this industry like all others. The companies that do so aren't just doing what's right for the planet and for the people on it, but also for their stakeholders and investors, because regulations are coming to this industry as they've come to others, and as the industry grows, those regulations will proliferate. So let's get to the interesting stuff. There are four basic effects acting on any launch vehicle. You have the drag, the lift, gravity, and thrust. Now, thrust is the emphasis of this conversation because thrust is what's produced by the propulsion system. But if you're interested, this is a good topic to dive into, and it's not unattainable for anyone that understands some high school physics. I'd note that density, gravity, ambient pressure, they all change with altitude, and they're independent of the vehicle design, so it makes for some interesting relationships between these four effects. Again, our focus is the propulsion system, so let's dive into that. There are three different types of propulsion systems that are most commonly used on terrestrial launch vehicles. That means vehicles that have to get off the ground on Earth and into the atmosphere or space. So liquid systems are typical for orbital applications. SpaceX, Falcon 9, the Rocket Lab Electron, Ariane, they all use liquid fuel and liquid oxidizer in separate storage tanks that are fed into an empty combustion chamber, sometimes force-fed by pumps, where they're mixed and ignited. These motors can be throttled. They're complex, but also very high performance, and hence why they are an industry standard. Solid propellants are used for boosters on some terrestrial launch vehicles, and they're also the type of motor that if you've ever played with a rocket model as a kid, like the Estes models, this is what they use. So you'll be familiar, the small cartridge is a solid propellant mix of fuel and oxidizer that fills the combustion chamber and actually comprises the combustion chamber. They can't be actively throttled. They can be passively throttled through the geometry of the grain of that little cartridge. But they're simple and effective, good performance, and also a little bit dangerous because they can't be turned off. So hybrids are a solid middle ground, and this is what bluShift Aerospace utilizes and a few other small startups that are in the micro launch industry. Fuel is typically a solid structure, like a cylindrical bore. This is a cross-section that you see in the bottom view here. And that bore that runs through the fuel is where you would pump your liquid oxidizer. So the hybrid is not the same hybrid as you would express in a combustion engine car with an electric power plant as well. This is a liquid oxidizer and a solid fuel grain, hence hybrid. You're able to throttle that liquid oxidizer, which gives you the ability to shut off the engine or throttle the engine by limiting the flow of the oxidizer. It makes it a little bit safer to operate than a solid propellant motor, with, depending on the propellants, typically lower performance, but more control and much safer for ground crew to operate. So when it comes to the propellants, there are more than a few options out there that exist. And currently operational green propellants include bluShift's proprietary fuel. So this fuel is completely non-toxic. It is nearly edible, but if you ask our CEO, Sasha, it might not go that well for you if you eat too much of it, and you have to chew for a very long time. And it can be handled by ground crew, as you see Sasha's holding it in this image here, but our ground crew deals with this fuel on a daily basis, and this is not the kind of thing that is new. We are not dealing with a new substance. This is a simple process from an agricultural product that has been derived into a minimally formulated it's a minimally formulated change from this agricultural product to what Sasha's holding in his hand here. There are other companies that create fuels from renewable resources, like Skyrora's Ecoscene, Orbex, and I think that this trend in industry to develop green propellants is moving forward at a good clip. Now, the future holds some things on an industrial scale and for large launch vehicles that could really impact the environmental impact of the launch industry. So there's green hydrogen manufacturing at a large plant in Texas that will hopefully change the paradigm for SpaceX when it starts using its Raptor engine for launches, and it could impact the BE4 and other companies if that becomes the new standard. For bluShift and other small launch companies, I'm sure we'll continue to develop our green propellants. But as far as we understand, bluShift's propellant is the only completely non-toxic and carbon neutral biofuel in the launch industry at the moment. We may change our elements of our propulsion system and of the propellants that it uses, but the general principle is what we expect to be able to move forward to for our first space launch and for our first orbital applications. So there are other consumables in launch vehicles, but they take up a much less significant part of the effort. So there are fire suppression fluids. There are consumable thermal protection systems like cork and ablatives like cardboard. There's also insulators like 3D woven felt. Now, it sounds like something grandma would make for kids on Hanukkah, but actually it involves a complex design and manufacturing process to effectively insulate high temperature components from critical spacecraft structures. These thermal protection systems are typically consumable. They are meant to make the rest of the vehicle more survivable. And then you have pneumatic actuation fluids as another example of consumables, but there are numerous others. They all are less relevant to the environmental impact and to the environmental sustainability of a launch program than the propellants are, though. So the second bubble at the beginning of this presentation talked about vehicle design and how the impact on sustainability is there. But before I start talking about what these major structures are, I want to explain why they might look the way that they do. And this is partially driven by Tsiolkovsky's rocket equation, which basically, I won't spell out the equation in depth here, but if you look at the part in the parentheses, the m naught over mf, what it's saying is that your initial mass over your burnout mass, which is the mass of the vehicle after all of the propellant is expended, is a very strong driver of the change in velocity of the vehicle. Now, what that means is it's not a revolutionary conclusion. Reduce the weight so that you can go faster. Reduce the weight that is not part of the propellant system so that you can go faster. So these large structures like oxidizer tanks, the aerostructure, combustion chamber, and the nozzle, they make up most of the burnout mass, that MF, that final mass of the vehicle as it's flying through the air. And before it takes off, the majority of the mass should be the propellant. So basically, the more of your propellant you can use to convert that chemical energy into kinetic energy, the faster your vehicle goes. These structures end up being very large and very thin wall, which means they're also quite expensive to manufacture. They have low factors of safety to allow for that MF to be as low as possible. Now, that low factor of safety also means that they are difficult to manufacture and susceptible to damage. Reusability has been on the forefront of development in aerospace over the last several decades, and the progress that's been made is huge. It reduces the cost, and it also reduces the environmental impact because manufacturing these composite and metal structures takes harmful chemicals and toxic substances. So if you can minimize the number of times you need to produce tanks, airframes, and nozzles, this has a major impact on cost and sustainability besides vehicle performance. So the downside to doing this, it's cost, time, and risk of failure at those low factors of safety. So let's go a little bit further into the vehicle design. How do we reduce that MF? There's some specific methods that are being used in the industry right now. Pumps are not new. Something that is a little bit newer, though, is the use of e-pumps. And Rocket Lab is a company that I admire for pushing this technology forward. They use this on their Electron rocket. They use an electric pump to pull the propellants into the combustion chamber, allowing the tanks to be thinner wall because they're under lower pressure and reducing the overall weight of the vehicle. Many companies have been using composites that are designed for strength in the critical directions in the vehicle. bluShift used a little bit of composites in the past, though our tanks have been metal for our first launch vehicle. we expect that in order for us to reach our orbital objectives, we'll be using composites extensively in our vehicles to reduce that MF and allow us to get to orbit. And then finally, there's new design tools that have really blossomed in the 21st century, like topology optimization and generative design. This is an example of a Aerospike nozzle that I'll discuss in a moment from a company called Hyperganic. It's their design, and EOS is the company that printed it. They're both German companies, probably not too far from here. This technology, these design tools, they basically reverse the process. So instead of having to generate a CAD model and then analyze it and remove unneeded materials, you start with engineering requirements as inputs to an algorithm that generates the design. And it requires a lot of human input still. But what it does is it makes more of an engineering problem than a CAD expertise problem. So yeah, what does the nozzle do in general? The nozzle is the business end of the rocket, right? And through Newton's third law, it propels you forward. So there are really two components of the thrust force. And that's the pressure thrust, which is basically the forces acting, the small green arrows that you see acting on the walls of the diverging section of the nozzle. And then there's also momentum thrust, which is the effect of throwing something in one direction, causing you to move in the other. Now, if you throw a lot of very small things, propellant particles, very quickly, you generate a good amount of thrust. So flow reaches the speed of sound at the throat of the nozzle. That's the converging section, the narrow where the point comes together and then separates. That point where it comes together is the throat. And at that throat, you hit Mach 1 in the flow, and you also hit the highest heat transfer rate in the combustion process. So this area has been the focus of materials research and cooling system design for decades. Nozzle throats are often graphite, but film cooling and cooling via recirculation of propellant is also common. You can see the heat transfer as a function of the distance along this nozzle here, and where it increases and decreases at the throat, it is highest. So nozzles are interesting. It's one of my favorite things to discuss when it comes to vehicle design, because there is an industry standard right now that seems suboptimal, and I'm going to describe why it maybe isn't actually suboptimal. So rocket nozzles, what you're doing with that expanding section is you're trying to allow your exhaust gases that propel the vehicle forward to perfectly fit into the exit plane of the nozzle. The problem is that what's driving that is the ambient pressure. So if the ambient pressure is higher than the pressure at the exit of the exhaust nozzle, as you see at the top, and your exhaust is pinched away from the walls of the motor, that's typical of launch from sea level. Then you have optimal expansion, which is the image at the bottom, where at some point during flight, the ambient pressure and the pressure out of the nozzle equalize. And then eventually, that ambient pressure decreases as you get to space, and you'll notice exhaust plumes on spacecraft expanding as they rise. So the nozzle works most optimally and has the best specific impulse, which is a measure of efficiency in rockets, at a specific altitude, which means that at all other altitudes, it's not as efficient as it can be. So there is a technology that's called the Aerospike nozzle. And bluShift has explored this. I've tried to manufacture one myself. We haven't yet tested it. But basically, it's at optimal expansion all the time because the exhaust gases are pushing inwards onto a plug. So the Aerospike is always at optimal expansion regardless of altitude. It's the perfect solution. Not quite. It does increase the efficiency of the combustion process and of the propellant system, but it's not quite perfect because you can imagine if you look at the image, you see the arrows showing where the exhaust plume is, and it is surrounding a solid piece of the nozzle. So there's nowhere for heat to go. So to get rid of that heat, you then need to recirculate propellant inside of it. You need to have active cooling measures, which makes it heavier and more complex. Basically, no one has effectively utilized an Aerospike nozzle in commercial applications or even in any production rocket as of yet. That doesn't mean it won't happen. There are modern advances in additive manufacturing, for example, in generative design and material science that may enable this implementation, giving whoever's able to do it a performance boost on their launch vehicle. So let's see who gets there first. There are notable mentions. I won't dive into these, but there's some cool propulsion systems out there that are worth looking into that aren't necessarily good for terrestrial launch. They're very good efficiency, but very low power. So you have the rotating detonation motor that JAXA just tested. Big credit to them. It's a very impressive system. There are ion drives that are typically used for satellites. They're smaller and more efficient propulsion systems than chemical propulsion. And you have nuclear propulsion, which you wouldn't want launching out of your backyard, but may be the best way for interplanetary travel in the future. So now let's talk about the business footprint, which is the part that I think I can speak to the most specifically when it comes to bluShift Aerospace. Like so many things, bluShift's story starts with Stardust. It's actually the name of our first launch vehicle. It was a low-altitude launch for a proof of concept of our hybrid propulsion system. That propulsion system was developed around the fuel, and the effort to develop the propulsion system was funded by a NASA grant to make this hybrid propulsion system with a green fuel into a modular, scalable system for implementation of future launch vehicles. The launch confirmed the analysis of the design that was carried out by Luke, the mechanical engineer at bluShift, and the vehicle architect. So his flight and propulsion models accurately estimated performance, and they set the foundations for the larger vehicle that we're working on now, which is powered by a scaled-up version of this same propulsion system that was used in this launch vehicle. So what else can we learn? What is the environmental impact of design decisions? These are questions that we ask often and systematically as part of our testing cycle. What do we need to learn to give our customers what they want, and what is the simplest way for us to learn it? Now, this is not just a question to make the engineering process more efficient, but it is a question of sustainability too. bluShift has found, and I think many companies find, that when you're flush with funding, there also tends to be more waste. By staying small and staying lean and sometimes pretending that you don't have all the resources, you come up with novel solutions that give you a simple approach to a problem that you may have otherwise dumped unnecessary resources into. So what we need to learn to give our customers what they want, we figured out how to do that with simple industrial metals, 2D cut plates, and you see an image of our first motor test of our 24-inch Marvel 2.0. That's about 0.6 meters across below. And there was we barely even needed to use CNC milling beyond 2.5 axis. So this was a very simple design that produces the thrust and performance parameters that allow us to develop the motor further. So yeah, what do our customers really want, and what is the simplest way to give it to them? Our answer to that is Stardust Rogue Beta, which is the launch platform that will utilize the Marvel 2.0 propulsion system. Ultimately, our customers want us to be able to launch off the coast of Maine for polar orbit launches, and we know this for a fact through doing research with potential customers. Environmental concerns actually haven't turned out to be a paramount in most of our market research, but we have secured a paying customer launching student payloads that stated that their priority is sustainable launch options. So even though this isn't an industry priority, we've already identified customers that are willing to work with us specifically because of our green propellant. So we need to grow fast enough to satisfy potential customer demand, because what our customers really want is to be able to launch their payloads. And the market is booming and competition is growing quickly to try to fill that void. Simple, scalable design of Stardust allowed us to move on to Stardust Rogue here. Now, Stardust Rogue is also meant to be a scalable design, and the propulsion system is meant to be the same as our orbital application. So the ability to grow with the industry, we're setting ourselves up to do that now. We have a motor that we're working on for our suborbital launch platform that doesn't actually get into orbit or space, but does it does get into space, but it doesn't stay in orbit. This same propulsion system, the one that I just showed you an image of us testing, is what we intend to use on Red Dwarf, which is our orbital application. There will be 7 motors on the first stage, and the second stage that uses a single motor. And planning for that now means that we have more of a chance of giving our customers what they really want in the future. So bluShift's mission, to provide research and customers with more control, lower development costs, and an Earth-friendly way to launch nano payloads to space. And our vision to empower humanity's access to space, to explore and develop our space economy while safeguarding life on our planet. This is our identity. This is who bluShift is. And we intend to maintain majority ownership with the founders and the employees so that we can maintain this mission and vision into the future. Funding for us has come from federal and state grants, including NASA and the Maine Technology Institute, for which we're extremely grateful, and has allowed us to become the company that we are today. But crowd equity funding is the primary funding source since the launch of Stardust, and it allows us to maintain this sustainable outlook on the future. But we believe that by acting sustainably now and using this crowdsourced equity rather than investment from sources that might dictate our focus, we can maintain a company that will be valuable into the future and viable into the long-term future when regulation and environmental priorities get to this industry as well. We've raised over $1 million on WeFunder so far, and that's helped fund projects like this one here, where we'll show you our latest engine test, a 20-second burn of Marvel 2.0 that we finished just before the next iteration of testing that we hope will happen in the coming months. We wanted to push the motor to its limits because this hardware is mostly being retired, and everything held up except for a little bit of heat shielding on the test walls. So thank you so much for sitting through this presentation on advanced propulsion. If you would like to learn more about bluShift Aerospace, go to blushiftaerospace.com, or feel free to contact me from my contact info on the slides. Thank you.